Hi, Josh. Can you solve this problem? A ladder is basically resting vertically against a wall that is perpendicular to the ground. It begins to slip and fall to the ground with the bottom of the ladder moving directly from the wall, and the top of the ladder always touching the wall. What path does the midpoint of the ladder trace?
So a version of this problem was used in an Oxford interview. So first, I will just sketch a quick sketch of the problem. There is, oops, very big. Here's our wall and floor. There. There is a ladder.
Yes.
Then let this midpoint be somewhere here.
That's the midpoint
So
of the ladder.
if the ladder slides down, sort of like this, what path will its midpoint reach? So that is the problem.
Yes.
So using the same diagram, no point here. Let the ladder be in, let's say, this certain position where it's already falling. So we will see what happens. And its midpoint will be here.
Yes.
Since the wall is perpendicular to the ground, let's put the label here, it's perpendicular. So this is a right triangle with the wall, floor, and ladder make a right triangle. So this is the midpoint. Those two are equal. So in a right triangle, something special occurs. This is a right triangle. Oops. It's circumcircle. This semicircle, and then this is the full circle. I'm sorry if my drawing is bad, but I think they should cover it. The hypotenuse
Straight.
is the hypotenuse is the diameter of the circle because
Right.
yes,
Hypotenuse.
hypotenuse. So if the center is the midpoint of this hypotenuse, which it is, then these two segments are equal. If we draw a line from the vertex to the center or the midpoint of the hypotenuse, this segment will also be equal. Yes. So hold on. Mm, Here, think this can be proved both ways, and then the converse can be proved. Ah, yes. Okay, so using this fact, we can. I'll just move this entire thing to the right. Here. Oops. I can somehow inscribe this. Oops. Oh, um, yes, it looks about uninscribed, and that looks about eccentric. So this segment, what color? This segment will be congruent.
Those
So-
two segments are all congruent.
If we slide down, I'm using a thinner line. Oops. Since the ladder's length hasn't changed, then this length still equal. So since the yellow segment length is equal to half of the ladder's length, and the ladder's length hasn't changed, this yellow segment is also congruent to half of the is equal to half of the ladder's length.
Ladders. Yes.
If we keep going on, etc. Oops. Then select one go away. Sort of like that. We will be able to form, I'll put it on the left. This is the wall and the floor. Okay. So these are the yellow segments that will be formed. Here first, and when the wall is touching the ladder.
Oh,
Then as the ladder falls, wait,
I thought this. Yeah, the yellow segment.
as the, I will just highlight the yellow segments because that's all we need. The yellow segments, since
So the
they,
length of
they
the yellow
yes,
segments are constant.
constant. So what is the locus of these points? These are the mid, this is the midpoint because I just defined the yellow segment to be from the right angle where the intersection between the wall and the floor to the midpoint. So this is
One
the
line up, one
midpoint.
yellow.
Ah, yes. It's the midpoint. One yellow line down.
Uh,
So the definition of a circle is that it is the locus of all points that are equidistant from a single point. And it appears that this midpoint is equidistant from the intersection. So this curve, what is it?
the length of the yellow segment is actually the
Yes, it's half of the hypotenuse.
yes.
So since this must be part of a circle, and since this angle is 90 degrees, that's a quarter circle.
And actually yellow segment, the length of the yellow segment is half of the diameter, therefore it is the half of the
Oh,
diameter.
it's not really part of the circumcenter
Yeah, but if it's half of the diameter, is it half?
of the circumcircle
No, half of the diameter.
radius.
Radius, yes. It's really the radius. So
Yes. So there's another way we can also prove this. This will be a little more mathematical. Okay, there is. Oops.
you can put it on the other side. Do that. So based on the so we can see it also on the other side. And, uh, and then find better with your
These are ladder a specific point. This is the midpoint. Let the length, I will, let the length of the ladder equal L. So therefore, since this is a midpoint, these two segments are equal and their lengths are L over 2 and L. So if we draw altitude, we just put the right angle. will be necessary here. Draw an altitude. And then in turn, draw an altitude from the midpoint to the wall. So then this will be parallel. So that's of course perpendicular. So this is parallel. That will be a right angle. And actually that's because of their definition. Don't you put this.
No, you put it for clarity.
Yes. So let this be y, this be x. I mean, I'll just use a different color. Let this be y, this be x. So if this were a Cartesian coordinate, the midpoint displacement is negative x, y. It can also be x, y. It doesn't really matter because anyway, by using the Pythagorean theorem by PT, oops, what happened? It got too thick. It got too thick. By PT,
Here.
the square root of, I know. I don't need the square root now. I usually use square root. X squared plus y squared is equal to L over 2 squared. If this doesn't remind you of something, I will just show here. The equation of a circle is x squared plus y squared equals r squared. So in this case, L over 2 is the radius. So going back to earlier, the yellow segment will be the segment from that point to the midpoint, the intersection to the midpoint. And since this is congruent, actually we can, it's not all, it's also provable. If we don't know what a circumcenter is, then this will be x and this will be y. Using Pythagorean theorem again, the yellow segment is still um x. It will sort of look like this. I can't explain it well. Uh, what will this be? Let's just be z squared. So if L over 2 squared is equal to z squared, there are no negative lengths. Therefore, z is equal to L over 2. So if z is equal to L over 2, it defines a circle. This equation, x plus y squared is equal to L over 2. Mm, mm, Wait, I will make it bigger. Can't really see what's going on below. There. And then, yes, won't be seen anyway. Also, if we draw once again another line, sort of Cartesian coordinates, Cartesian axis.
That's why the yellow segment is very so more slant.
Yes. This is the ladder. It's the midpoint. I can draw a yellow segment from here, but in this case, I will extend it until its length is equal to that of the ladder. So imagine there was a separate yellow ladder that would just fall down. So in this figure, it sort of looks like this. Oops, it's too wacky. Then so the yellow segment, the yellow ladder will just fall over. Since this is since this is the base is where it's sort of fixed. It's not really fixed, but in real life it will also be fixed. So this will be a circle because these are congruent. Of course, the length of the ladder. So that must be a circle. Because like
The
earlier,
midpoints,
Yep.
the midpoints also will
the midpoints will
make
also
also
make a circle.
a quarter of a circle.
Yes. So
And here you're proving why did you make it longer?
because
The red line
I was
is
I was just about to say, uh, the red
before
the length of the length of the red segment is equal to
equal
the
because it
length.
makes a rectangle, right?
No, that's because I defined it that way.
And okay, and then it's also because it can make a rectangle and then so the
Uh,
on that figure the red segment and the yellow segments they have equal lengths.
wait, so I already proved the midpoint of the yellow segment would be traveling in a circle. Wait, where is it? Midpoints.
Yes.
Sort of, so it's sort. I don't really know what the term will be, but it's sort of parallel to
There
the.
will be
I know they won't be overlapping since the red ladder is just
they were
reflected.
overlapping in their midpoints on the blue dots. Correct? Their path. Can you make another so they can picture another yellow and another red? Yes. There. Nice.
So as I was about to say, the path formed by the midpoints of the yellow ladder it forms a quarter circle.
And also
Eh,
the red. No?
No, we don't haven't proved that yet. We haven't proven that
Yeah,
yet.
that's what you will
So
do.
that's what I will prove.
Okay.
Since the red ladder is just reflected upon the midpoint of the red ladder. The red ladder is actually the red ladder is reflected upon the midpoint of the yellow ladder because the yellow ladder is how I defined it. It will be a reflection of the red ladder upon its midpoint, but instead of its vertex being its endpoints being free, one of its endpoints is stuck to the base of the wall and to the intersection between the wall and the floor. This point.
Yes.
So both of them will travel. They will the sort of carjack. They will just they will travel the same path essentially.
Yes.
That will be the semicircle, the quarter circle form. Of course, in real life, the sliding ladder would be slower because there's friction. But if we ignore friction in this case, so here, wait, I will just show you. Uh, yes. So
Here.
this is an animation I made in GeoGebra. There is And Alt Shift H. Okay. So as you can see here, I already plotted where the ladder will go. And these are the points, the blue points, and the final red point. Those are where the ladder's top part will be, top endpoint. And then the red points are the bottom endpoints. Yes. And the gray gray points are the midpoints. So as you can see here, they form a circle. I can prove that. Where is the circle tool? Circle. Yes. Circle tool, start here. Oops. Then, yes, it forms a circle. Yes.
Yes.
Okay, so now this is our animation. So this is, wait, I'll just stop it for a moment. I forgot to explain it. It started automatically. So here, let's put my animation someplace. There. So the black point is the example sort of head, example top end point, and then the what's this color?
Which one?
This one. Sort
Red.
of
Red.
yes.
The
The
blue are the top point, the end point,
yes.
and the red are
End point.
the red are the
Yes.
bottom end points.
Yes, in this case, the green here is an endpoint as the midpoint. So I can show the contrast. The contrast, the gray points, the black is the top and the reddish color is the bottom. So
Blue. The blue are the top. Josh is partially colorblind.
no, this one. This one is the
No.
endpoint.
Red. Those are, let them all be red. Then.
No, this is
To
so
simplify.
yes.
So the blue are the top endpoints and the red are the bottom endpoints and the gray are the midpoints of the ladder.
The blue segment here is the ladder itself.
Yes,
It's
that's
falling.
how it's falling.
And that's the path traced by
Meaning
the
the top
midpoints.
top portion is always against the wall while it's falling.
Yes. So another interesting fact about this appears to be a curve formed by the ladder falling. This one, there appears to be a curve forming. So this curve is called the ladder envelope. It's the path formed by the ladder. If you just make many of them. And the ladder envelope is 1/4 of what is called an asteroid. So if I'll just demonstrate a bit. Where is the escape? Stop share and in a whiteboard. If there is a circle and then there is another circle, and then the circle travels along, then it has the center. I forgot to prepare another animation for this. Anyway, so imagine this circle moves along the inner surface of the other circle. So what is the path traced by this center? If it's moving fast enough, it will sort of look like this. Yes, sort of like that. So if there is one cusp, it's a cardioid, and then a nephroid if there are two. Three is a deltoid. This in this case, it's an asteroid because there are four. So this 1/4 a portion, that is the curve formed by the ladder.
Is that
Yes.
related to the Brachistochrone?
Yes, in some way. It's a distant relative. The Brachistochrone is formed when there is a this this is a straight line, then there is a circle. and there is a center here, and then we make this center, we make this circle move, roll along the straight line. It will form a curve like this, sort of like that. So this curve is called the Brachistochrone, and then half of it will be called the Tautochrone. If we have a Tautochrone like this, and then let's say this will be another perfect. The full length is the Brachistochrone. The half portion is just the Tautochrone. This is the Tautochrone. This is a straight line. And then this is another path. Let's say a 6-degree polynomial. The tautochrone will always be the fastest route for a ball to travel down. If the ball will travel through the straight line or the ball will travel through the tautochrone will always win. Yes. This is a interesting problem indeed.
Do you want to show them how it will trace?
Oh yes. So where is our little line? So I will put it somewhere where I can find it. And then expand maybe somewhere where I won't accidentally select something. There, here, show trace. Shown, yes. So, okay. 1, 2, and 3. Wait. So that's its trace. It traces a circle. It's just not very accurate in the top because it's moving fast. There. This is our
Part of the circle.
yep. So thanks for watching. I hope this was interesting and the solution was understandable. Thanks for watching.